the recording and going to share desktop. Okay, you see the desktop okay? Very good. I'm hoping more students show up tonight because I wanted to demo with you guys. So we'll do this class participation and context switch sample when more people show up. Are there any questions before we start our session? Yeah, one thing I did note that the recording of Tuesday I didn't get until today. I checked all day yesterday, but it never showed up. It finally showed up this morning. So they're out there now. Sometimes they take a little more than 24 hours. I'll do the CC confer question after we do the class participation one. It's just we need about 5 or 6 people to do that. I thought we would discuss the special extra credit programming project towards the end if we have time, and how to do chapter 3 question number 3 homework. It was the one about the forks. I just wanted to quickly review with you, and then we'll start chapter 4 discussion. So what I'm going to review is the process state transition diagram. Good evening, Fawad. Welcome. The typical process goes through these states, and it's maintained in the process control block what state that process is currently in, and there's a queues for each of the states. There's data structure queues, so the operating system knows what process is in what state, as well as in the process control block, the state property has the state of the process. So I got new state, and new usually it happens when you in Windows, if you double click on something and you see the little hourglass, the long-term scheduler or master scheduler is deciding if they can put that process in memory or not and give it resources. Okay, if it can't, it'll stay in this new state until it can, and that's what the emit is. These are directional arrows as to which way the process flows from state to state, called the transition arrow. Ready means it has all the resources it needs except the CPU. Okay. The dispatcher is the short-term scheduler, and it'll pick a process and basically set it up to run on the CPU, and it'll execute until a couple of events may occur. It'll execute until a timeout interrupts the process, or a service request, it requested service, or it exited, or it abandoned for some reason. Okay. When it times out, it goes back in the ready state, and then the dispatcher decides which one to go again. Okay. When it's blocked or waiting, that's another way of calling this state. It has to wait until the service has been completed. If it does complete, then we move it to the ready state. Okay, the intermediate scheduler, this is stuff that's in memory right here. This is stuff that's out on disk. So if we need to get more memory or resource and a state, basically a process is blocked, we could suspend that process. So that's an action that the intermediate scheduler, or some authors call it swapper, performs. And then the same thing could be true in the ready list. We could have a low priority process, we swap it out, suspend it, swap it out, and it goes into a suspended ready queue. And then we can resume it. If it's in a suspended block state and the I/O completes, it'll get pushed into the suspended ready state. But the dispatcher never sees this. The dispatcher always looks into this ready queue to determine what to run next. Okay, I reviewed what we talked about last time. Are there any questions on those? See, we got Daniel came in, Bang came in. Good. And Kang came in. Welcome. Sure. The what? Oh, yeah, we're going to talk about that. We're not going to talk about it tonight, but Chapter 5, 6, and 7 really deal with those kinds of issues. And we will go in depth on that. Okay, good. Normally, the user sets a priority, and then the operating system can modify that priority, or not, based on the operating system. So that's kind of the short answer. Now that we've got enough people, I think we can do this. So let me get that up, and I'll explain what we're going to do. And I'm not sure exactly how it's going to work, but we'll try. We need 1, 2, 3, 4, 5, 6. How many people do we have? We have 1, 2, 3, 4, 5. Okay. So we'll do this. We'll assign one person to both of these handlers. Okay? So what's the idea is I'm going to take you through a context switch and demo it. So it's hard to see this, but the events, let me just show you the events. The events are going to be, we're going to have program A executing. It's going to time out. The dispatcher is going to come in and choose B to execute next. And I'll take you through everything that it does. During B's execution, A's I/O is done. Wait a minute, it doesn't time out. A is executing, it requests service. This is wrong. It requests service, i.e. a record or a file or something. Okay. During B's execution, A's I/O is done. Since B didn't complete its quantum, the dispatcher will restart B with an adjusted quantum. What I'm trying to describe here is typically when, in this example, when the process is running on the CPU and some external interrupt occurs, normally we would return the control back to that program to finish its quantum, but we could preempt it. So we'll take a look at that in other cases. This case, we're not going to preempt it. We're going to allow it to run, and I will take you through that. Okay? Because we have algorithms later on that discuss that. But what I'm trying to show you here is how context switch works. So who would like to be program A? I need volunteers. Megan. Okay, you're program A. Who would like to be program B? Daniel. Okay. Okay. Who can count really good that hasn't volunteered? I need a timer. Kang? Can you count? You're hardware, okay? You're hardware. You're a very significant piece of hardware, too, I want you to say. Okay, I need the disk device, another piece of hardware. So, Fang, can you be my disk drive? Okay. And we did pick up some people. So I need a service handler. Albert, could you be the service handler? Okay. And I need, since somebody else came in, let me see who came in. Oh, I missed Fawad. But I don't know if I'm pronouncing it right. How do you pronounce your name? Thank you. Fawad, can you be the I/O completion handler? Okay. Okay, so here's what's going to happen. I'm going to be the dispatcher. So I'm going to start on the CPU, and we only have one CPU here in this thing. So I'm the dispatcher, and I'm going to load program A to run. Okay? So right now the operating system is in privileged mode because I'm in the kernel. So the CPU is running in privileged mode, and it checks the program control blocks and finds A is in the ready state ahead of B. So I'm going to start up B. So I look down here and, excuse me, I'm going to start up A. I look down here, Mega, pick a number that you'd like to be at. You know, any number, 3-digit number would be fine. 1, 2, 3, that's, okay, that's the address that I'm going to start the CPU on, okay, is that address. So I set the timer. Kang, that's you. And we'll set it to 40. So once I start the timer, Kang, I want you to type in here. I'll give you an example. You'll type 40. Well, that's not 40. You'll type 40, and then wait a couple of seconds. 39. Wait a couple of seconds. 38. So you're going to count really slow down to 0. When you hit 0, you're going to say interrupt. Okay? And you're going to interrupt the CPU. You got that? No, it could be 2 seconds. Okay? It doesn't have to be 100% accurate. We're just demonstrating. Okay, good. Then what's going to happen is when I say this, I'm going to set the timer, and I'll say start timer, then you'll start counting. I'll put Mega in, and Mega's going to be starting at 123. Okay, and I'll be changing this to Mega. We're not counting yet, Kang. Then, Mega, what you're going to do is type 123, 124, 125, 126, 127, etc. Because you're executing. And I'll set you in non-privileged mode. So you'll keep executing. Okay. Now, before he gets to 0, I want you to say this or type this. And that is a soft interrupt construction that you want a service. Okay? When that happens, what I'll do is I'll say, oh, we have an interrupt. So I'm going to take, it's a service request. I'm going to take Albert's, and I'm going to put Albert in. I'll put Albert in, and what Albert you're going to do is say this. So you're going to say something like this. Save A's state. So you're going to say save A's state, because that's who's running. Or you could use Mega if you want. And that will save whatever number she left off with. I'll put that number here, whatever she left off with. Okay. It disables the interrupts. Okay, so we know we're not going to get interrupted anymore, Kang. So you could just stop counting down at that point. Okay, you can stop counting down at that point. All right. Now, what will happen will be, Albert, you're going to, I guess I need another person. Do I have another person? No, I don't have another person. What we'll do, Albert, is normally the handler, this service request handler, would pass control to the I/O system. So you're going to be both. And what you're going to do is you're going to say start I/O. Okay? So, Albert, at some point after you save a state, yeah, you'll say start I/O. Bang! Are you there? Bang! Okay, you're going to start counting down. And what you're going to count down from is, let's say, 20. Really slow. So you're going to count from 20. Oops. Make sure I get up here. You're going to count down from 20. Same thing. You'll type 19, 18, etc. When you get to 0, you're going to say int, because your I/O completed. You have done the I/O. You moved the request into Program A's data area. That's what you were doing, because Program A wants some data. Is that clear? Okay. All right, and then we'll do the same thing for Program B. The difference, though, is Program B is going to time out. We'll do that. Daniel, when you're running, you're going to get interrupted. You're going to do the same thing. What address do you want me to restore for you? 222. Okay. Okay, 222. Okay. And then you're going to go 223, 224, etc. And probably what I'll end up doing is I'm not going to do it this way. I think what I'm going to do is, since B didn't complete, it's quantum, the dispatcher star speed with it. I'll tell you, Kang, what the new quantum will be, okay, for that. And then we'll go all the way down to a timeout of the timer. Okay. All right, I think we got it. So let me start it off. I'm the dispatcher, and I'm the guy who's kind of keeping track of what's happening. Okay, you ready to start? I'm going to load A. So I fix the queues up. I take the 123. Oh, I start the timer at 40. So now it's going. And then I load 1, 2, 3. And this is Mega. And you're running Mega. And at some time, Mega, you're going to request your interrupt. Okay, stop, everybody. Interrupt occurred, and the next address to fetch was, let me go back and look. I don't remember what your number was. You were at 127, so the next address would be 128 or 129. Let's pick 129 because 128 was probably the interrupt. So what happens is the hardware does the following. The hardware saves the 128, okay, and loads in, this is a I.O. Service request, loads in Albert's address. So now Albert 120, you're going to save the state, Albert, right? First thing you're going to say? Go ahead and say it. Type it. Albert, are you still there? I guess we lost Albert. Kang, you're counting down. I'm going to stop your timer, so don't count anymore. I don't see Albert. He's not there. So I'll play Albert. What happens is we're going to save this state. So instead of it being 1, 2, 3, the new address to load is 129. Okay, and all of the registers get saved. Oh, scroll down, I'm sorry. I am scrolled down. I'm not sure what you mean. Oh, you mean here? No? Scroll up. Yeah, okay. Oh, I see it. Thanks, Albert. Save a state. Good. So, we saved the state. There's A. Albert's also going to fire up the disk drive. Start I.O. Okay, Fang, you're counting down very slowly from 20. Okay, now, what happens, Albert, is you, when you're done with your work, you call the dispatcher. So right after the I.O. device was, right after the I.O. device was saved, you would call me, the dispatcher, okay, and I'm deciding what to do. So I'm going to put in B, Daniel's program. Okay. So Daniel, you're going to be running. So I'll, Daniel, before I put your address in of 222, Kang. I'm going to start the timer again at 40, and now you're running. Okay, and I put in 222 in non-privileged mode, and Daniel, you're now counting your addresses. And Fang, where are we counting down from 20? Where are we? Oh, you didn't start counting. Okay, count down faster. Start at 10. Fang. 10, 9, yeah. Good. Stop. Stop. Here's the interrupt. It's a hardware interrupt now. It's not a software interrupt. It's a hardware interrupt. And Daniel left off at 234. So next instruction would be 235. Okay. We would save the state. Fawad, you're the one who is running now, so you would say save the state of B. Go ahead and say that. No, not, yeah, 225, that's good. Yeah, that would do it. Save that address. So that would be 235. Good. You also turned off the timer, so the timer is no longer clicking. Where was our timer? What number was the timer at? Oh, you already timed to 0. Wow. Okay. Yeah. Can't stop. Yeah, we probably would have hit you before you were done timing down. Let's say we gave this program B. Oh wait, I put it in the wrong place. I put it in megas. I shouldn't have done that. See, the operating system isn't very good here. It was you were 142. Is that what you have there? 192. You were 192. And Daniel, you were at 2 what? 234. Thanks. Okay. So I save the status, and also what I would save is how much time I gave, how much of the quantum I gave. So I'm going to set 20. I gave 20 units of quantum to program B, Daniel. So, Fawad, what you do is you're going to, from the completion of the I.O., what you're going to do is you're going to make sure that those things got saved. The data that got read in, got placed in the data area of program A, because that's who requested this record, is program A. So that data would go in here that you fetch from the disk. And then you would call the dispatcher. Okay? So who's running now is Fawad. You're running. So you do those things. You said save, didn't you already? You just call dispatcher. That's how you do it. Just call dispatcher. Okay. we save the state of the running program. Dispatcher. Okay, now the dispatcher is running. That's me. Okay, and what I'm doing now is I'm deciding I/O completed. As Fawad, I forgot to tell you that you needed to switch the status of A, excuse me, from blocked to ready. Okay, we forgot to do that. Then A and B would both be ready, but what I'm going to do is I'm going to load up B, let it finish its quantum, and we'll do a timeout. So, as the dispatcher, I decide to run B. So what I'm going to do is set the timer to 20. All right, Kang, ready to start? Start timer. I load up program B, so that's Daniel, and start Daniel running in non-privileged mode. So now, Daniel, you're running. Kang, you should have started at 20. I started the timer at 20, not 30 or 40. Okay? Start the timer at, you should be at 15 now. So say 15. Yeah, there you go. Good. And it's executing, and it's executing, and it's executing, and it's executing. Looking good, looking good, looking good. All right, it hit. So an interrupt hit. Yep. And the interrupts are disabled. What address were we at? 243 for Daniel? Yeah, 243. So we save the 244 address, and it's still ready to run, but we put it in the ready queue. Okay, it's still ready to run. It was executing. We put it in the ready queue, and who's handling it is the timer handler, and we don't have one. Bale came in. Bale, you're going to be my timer handler. All right? So you're here. You're running because of the interrupt. Okay? And what you say is save the state for B. So go ahead and type that. Okay, switch status for B to ready, because it was executing. So say that. Switch B status to ready. Okay. And call the dispatcher. And that's who's running now. And what mode is the CPU in right now? What mode? Privileged or non-privileged? Anybody? You bet. Because an interrupt changes the mode of the CPU from non-privileged to privileged mode. That's part of the hardware. The hardware does that. Very good. And that's a context switch. That's how context switches work. That's how the interrupt scheme works. And we took you through this example here. That program A is executing. It requested a service. Dispatcher chose B to execute next. During B's execution, A's I/O completed. Since B didn't complete its quantum, the dispatcher restarts B with an adjusted quantum. Exactly that process. Any questions? Is this clear now how this works? Yeah, if we were in a classroom, I would do something like having you people representing the software and the hardware, especially the software. You would be sitting on the CPU because that's a chair. You'd be sitting on the chair executing your code. And the hardware would be standing off to the side, periodically sending an interrupt by touching the chair. That's how it works, Kang. That's why you want to run multi-programming, because the CPU can be executing other instructions while the I/O device or any other external device is also working. It is like a pipeline processor. Yes, similar. Yeah, the thing about a pipeline processor is it could be executing an instruction while it's fetching the next several instructions, or interpreting the instructions. That's really what pipeline is. But I wanted you to see it. Okay. Now that we've got a clearer idea of this, let's look at the chapter 4. And talk about threads. Threads are fairly straightforward. They're not. There's only a few issues you have to worry about in threads. Okay, and I'll point out those things as we get them. Basically, it's the fundamental unit of CPU utilization. So basically, a thread is like a little bundle that runs on the CPU. I mean, that's really what it is. It's got some code, it's got some data, and it's part of a process. I mean, it could be the whole process. So here's a good example of a multi-threaded process. You have your program code, you have data, you have files that are open, you have registers, and you have the stack that you maintain for that program, and you got one thread running. Multiple threads, the key concept of multiple threads is you can see this has got a line here, and this has got a line here. Each thread has its own registers and its own stack. The stack would be data appropriate to that thread. There is shared amongst these threads is one set of code. So there's no code in each of these little threads. It's all being shared by the main program here. Same thing with data. Anything data in the main program is shared by all of the threads, and any files that are open are shared by all the threads. The only thing not shared would be the registers that are currently, the state of that particular register and any particular data for that thread. All of that is in this. So I could be running 3 threads of this program at one time. Well, it would just, if I have one CPU, it would work this thread, then maybe this thread, then maybe this thread. So scheduling a threaded system is much like a program, a process, one process, but it's just a tad more complex. But the key point I want you to come back with, because it's on a lot of tests, is that the code of the program, the data of the program, and any files that are open are shared by all threads. The things that aren't shared by the threads are the registers at the time and the stack that goes with that, right here. Okay? Is that clear? Okay. You got that, you're pretty good. Okay, so why would you go with threads? Well, more use of the CPU. You can share resources better. Economy over time, and then the scalability. If I don't have, let's say 2 threads won't do it, I go to 3. If 3 won't do it, I can go to 6. So it's very scalable. Okay, multi-core. Multi-core systems are putting pressure on programmers because they divide activities, they balance the load, they split up the data, they have data dependency, testing and debugging. All of these things are more complex in this environment. I think that's what he's trying to say. Has any of you programmed a, it would be called in programming terms, a reentrant program or recursive? Okay. Well, think about what you had to do for your recursive program, and think about having multiple paths of your program running at the same time. A little more complex. You could have a server architecture that handles those. And on a single core, he was trying to show you the different threads that you could run, and they don't have to be in that order. So now if I have 2 cores, I could run thread 1 and thread 2 on 2 separate cores, 3 and 4, 1 and 2, 3 and 4, etc. Or not, depending on my design. Most of the threading is done by user libraries. So all of these use libraries, these designs, because they want threads to be created by users and managed by users. Now, of course, you know it's not going to happen. It's going to call the kernel side to perform whatever request your particular use of threads is going to happen. So when they built the system, they wanted programmers to manage their own threads. But at the bottom of this is the kernel level activities have to occur to support those threads, because you don't want users getting to I/O devices, getting to memory, all of that without going through the kernel. Does that make sense? Okay. I guess it does. Thanks. I'm going to skip over this and talk about the threading models. There's 3 threading models for the operating system. when you design it. You can use many-to-one, one-to-one, or many-to-many. And you'll see what I mean by the next diagram. It's not that complicated. Okay. Many-to-one is Solaris, but we don't have Solaris anymore. This is many-to-one. Here's a kernel user level thread going to a singular kernel. Another user thread going to and calling a single kernel thread. So basically I have one kernel thread supporting 4 threads. This is simple to manage, but it makes the environment dependent on that one kernel thread of being very efficient. Okay? And some of these are going to have to wait for that kernel thread to be available. So this many-to-one model is kind of inefficient. One-to-one. Linux, Windows, and Solaris 9 and later use this model. So every thread gets a kernel thread created for it. So when I create a thread, I also create a kernel thread that would support that thread. So basically what we're saying is for every thread you got an additional thread. Any thread you create, you got an additional thread that the operating system creates. But it's very efficient. I mean, this guy doesn't have to wait for a thread to request kernel service. This thread, same thing. The issue, though, is you're doubling up your resources. Now I've got to keep track of not just my user threads, I got to keep track of my kernel threads that support each of those. Oh, I'm not going to do this. Okay, that's pretty good. Okay, the last model, that was one-to-one, is many-to-many. Now, the idea here is I have a certain number of threads, like a thread pool, and depending on which one's available, I would assign that thread to maybe this user thread. And then when it's done, it would be available and I can assign it to that thread. So in this model, I don't have as many threads to use up resources, but it's going to take a little bit longer because I've got to assign the thread to the user thread, and then when it's done using it, I can unassign it. So that little bit of management of these is going to take a little bit longer. So what you're playing off is this is going to take a little longer to handle the threads versus this one where you have a little more resource usage of your environment, memory, and your queues and all of that. Okay. Any questions on these threading models? Okay. It's many-to-one, one-to-one, and many-to-many. It's certainly going to be on the test. Okay, you could have a two-level concept. And it looks like HP Unix uses this concept where you have both a many-to-many and a one-to-one. And you could use it depending upon what circumstances you're running into. For instance, if you just have one thread, right, and you get one kernel thread. If you start to have multiple threads in your program, then you might go to this model. That's the idea here. Any questions? Okay. Okay. It's going to get to a more interesting area in a second. Typically, the thread library, like I said, is API support for programmers to create threads. Skip over that. I'm going to skip over that. And let's talk about the issues. Okay. The fork and execute system calls, you got to handle what happens there. How do you do thread cancellation or target the thread to be canceled? Is it going to be asynchronous or are you going to defer it? How do you handle signals? What about pooling threads? What about the thread-specific data? And how do you schedule activations? These are some of the threading issues in this environment, and we're going to talk about it. Does the fork duplicate only the calling thread or all the threads? What do you guys think? You would implement all, and someone else would implement the calling thread. Well, that's the issue. So it could be either way, or it could be that there's parameters in the fork that would specify one way or another. I mean, all of these are possible depending on how you implement it. Right, that's what we're getting to, Mega. The environment is a lot more difficult to manage, and especially you're allowing the programmer to try and control this. Okay, so now let's talk about how you cancel a thread, right? You basically, how do you terminate a thread before it's finished? So some other call, right, by another thread saying to this thread, we're killing you, we're terminating you. So two general approaches, right? You asynchronously cancel, terminates the thread immediately. So as soon as that hits, it'll terminate the cancellation or cancel a thread, and the thread would go away. Deferred canceling allows the target thread to periodically check if it should be canceled. So it's checking a flag of some kind to see if it should be done. It should be canceled. Yeah, Megan, you're right. There's locking that needs to go on. This is one of my favorites, is how do you handle signals? You know, when you write like a signal 9 or something like that to a program in Unix, that may need to restart. You want to restart the program. And you've got these threads. Well, which thread gets that signal? because you've got the level of a process, and now you have this next level of these threads running around. So all of it is, how do you handle it? So here's some of your options. Deliver the signal to the thread to which the signal applies, if you can do that. Deliver the signal to every thread in the process. Deliver the signal to certain threads in the process. Or assign a specific thread, this should say thread, to receive all signals for the process. So these are some ideas about how to handle that. And each operating system has their own mechanisms. But if you were designing an operating system, you would have to think about, especially if you allow threads, you would have to think about, how do I want to handle signals? How do I want to handle terminating a thread? I mean, that's all I want you to understand. I don't want you to come up with some fancy mechanism. But what you could do is, on your project, right, that you guys are going to be doing on an operating system, you could be telling me how the operating system handles signals with its threads. Another technique is thread pools. You create a number of threads in a pool where they await work. Slightly faster to service a request with an existing thread than to create a new thread. So you're talking about a performance improvement, and it allows the number of threads in the application to be bound to the size of the pool. In other words, you can't exceed whatever size of the pool is. So this idea of thread pools is a good one. But once again, it adds complexity to your OS. And you have to explain that to your programmers who are going to be using the API calls. So all of this has to be really explained well so that a programmer can figure out how to use it. You could have thread-specific data. Allows each thread to have its own copy of data. In other words, its own data that it manipulates. And it's useful when you do not have control over the thread creation process, i.e. when using a thread pool. Certain data you might need to understand if you're using a thread pool. So that's another thing to look for. Okay, so many-to-many and two-level models require communication to maintain the appropriate number of kernel threads allocated. So once again, many-to-many, right? There's a number, and then the two-level has a many-to-many. One-to-one is pretty easy. One-to-one is, I have one user thread, I get one kernel thread created. Well, scheduler activations provide what's called upcalls, communication mechanism from the kernel to the thread library. So you're going back up from the kernel back up into the API, into the library that was being invoked. The communication allows the application to maintain the correct number of kernel threads. Okay, so we're communicating up, back up to the user thread. What's kind of happening down in the kernel level. There's examples. We're almost done here. These are threads that are example of XP, which is, you know, Windows pretty much. You have your thread, and then you have your kernel thread. So you've got to schedule that, both of these guys. You've got these pointers keeping track. And then your blocks, your thread control blocks. And what runs is that thread. So your user space is what's executing here, and the kernel space is executing the privileged instructions here. Looks okay. Linux. There's more on that, but I'm not going to cover that because it's, and I'm going to skip that because you guys are going to be analyzing that. Okay, this is a good spot. I want to stop a second. There's not much in this chapter about scheduling threads. You notice that there wasn't a lot of discussion because chapter 5 talks about scheduling processes, and it'll go into scheduling threads. But if you think about it, let's go back to this diagram. When I schedule a process, right, the dispatcher, we went through that wonderful example earlier together. I look on the ready list, but what really runs is not the process, it's the thread that gets really executed. So I've got maybe 3 threads of a process, and if let's say 2 of those threads are executing, the other one is sitting here ready to execute. I just want to point out the complexity of this. I said, well, what state is that process in? So I tried to illustrate that here somewhere. Okay, so program A has 3 threads, A1, A2, A3. We're assuming 1 CPU with 2 cores. So A, as a process, is executing because A1 and A2 are executing. A3 is blocked. It's not ready. It's blocked because it's requested some kind of a service. So does that mean if any thread is blocked, does that mean that the process itself is blocked? What do you think? No, because part of it is executing right now on the CPU. The other is waiting for an I/O. So is it which state, that's what we're trying to get at, which state should a process be in when a thread could be in one of 3 or 4 states? That's the question that I'm asking you. It's how you design it. It's how you design it. All right? Mega. In this example, it's concurrent because A1 is executing on one of the core and A2 is executing on the other core, and it's executing simultaneously. Yeah. Or concurrently, I guess would be more than one. What word do I want to use? Simultaneous. I want to use asynchronous and synchronous mean something different. Let's do that. Asynchronous means it's not tied to a clock pulse. Synchronous, to me, means it's tied to a clock pulse. So when we talk about an asynchronous event, it's an event that we don't know when it's going to occur. Whereas a synchronous event is something that's typically tied to a clock pulse. So these 2 executing are executing synchronously. Okay, A1 and A2, if they're on different cores within one CPU, they're executing synchronously. A3 is blocked, so it's waiting for something. So my guess is it would be waiting for an I/O or something to complete, some kind of service. So it's not tied to a clock, it's asynchronous. It's tied to some event. Can a thread die during execution even when it's not finished? Yes. Yes, Mega, that is correct. And it could die for many different reasons. Let's go back and look at that. It's somewhere back here. In the issues. Yeah, thread cancellation. Terminating a thread before it is finished. Well, here's one possibility. One of the other threads, let's say we only have 2 threads that are executing this program. One of the threads did a divide by 0. The other thread is executing. What do we do with that guy that's executing right now? The other one died. So do we terminate the one that's executing because the first one died? And that would be this event, the asynchronous cancellation. It's not timed together. Okay, that's one example. Did that make sense? Why? And that's what you might want to do. Because it gets more complicated. If you say, okay, I'm going to leave the second thread running and the first thread I'm going to get out of the system, well, maybe the first thread is the, quote, parent thread, and the second thread is a child thread. And you can have parent-child. Because usually you have some main, all programs start with main, right? So they start with main, and then they could split off into multiple threads, depending on their own programs, whether they're doing threading or not. The other one is this deferred cancellation, and it allows the thread to continue, but it should check if it should be stopped. So another one might be, the same example, thread A somehow aborted, and then thread B, we check periodically to see if thread A has been aborted. Something like that. It's complicated, is what I'm trying to get down here to. And what you want to do is keep this as simple as you can, because it's difficult enough to think about how do I get my threads synced up again. The producer-consumer, is it possible that both of those are threads of a program? Yeah. Yeah. So, yeah, that could be that the producer is a thread and the consumer is a thread. Yeah, that could very well be. So if the producer dies, there's nothing put on the buffer because the consumer has taken everything off the buffer and is waiting for the producer to put it back on the buffer, and it doesn't. So there would probably be some communication of that event, and then my guess is it would be a deferred cancellation, and it would say, oh, I can't do any more, I'm going to terminate myself. That would be a possibility. Okay? Is that clear? I mean, the reason he doesn't go into too much depth on these threads is because it is, yeah, there's nothing else to consume. But it doesn't know that by looking at the buffer. It really does. It just knows that it's empty and it's waiting. It doesn't know that the producer died. So somehow the dying of the producer has to get known by the consumer. That's why I was saying about some mechanism needed to be set up so that the consumer could check to see if the producer was still active. Same thing on the producer. The producer fills the buffer and is sitting there waiting for the consumer to take it off, but the consumer died. Same issue. But yeah, that's a good example. Okay. So here's another example, right, where I have, looks like I've got A1, A2 ready. I don't see A3 anymore. So the processes state is ready. So this looks like there's only two threads in this example. A1 and A2, they're both ready. So the whole process is ready. And what I'm trying to explain on this example is we still use this concept. We still use this concept to dispatch a process, but we tweak it right in here. It would be these three states. We would tweak it to handle threads and thread scheduling of that process. Okay? But I wanted to keep it simple. And this is a simple process state transition diagram for programs with one thread only. Just makes it easier to understand. Okay, so I have in my system block, I have my pointer, right? I've got all of my process control blocks, and I also have a thread control block. So I would have a thread control block 1, a thread control block 2, pointing to all the threads of my process. And then I would have a thread ID that went with that thread, and the thread state, and I'd probably maintain these three states of the thread. And then I would have a pointer to the system stack, right? The stuff that's shared, shared data for all the threads. Any questions on this data structure? Okay. All right. We got plenty of time, which is good. I put this in the agenda. I don't know if you need to see this, but how to do Chapter 3, Homework 3, work question. Does anybody need assistance with that question? I was going to share something if you need help. So let's look at the question. Okay, Kane. Sure. Yeah, because I'm not sure if people really understood what's really happening here. Okay. And remember, the diagram was not there. I had to go chase it down. And so I put the diagram that I believe he was referring to here. So what I did was I copied this and I typed it into my Linux version. So I'm going to start my Linux machine in my virtual space. Remember, I said you should play with these different operating systems. So I'm going to start up Ubuntu, and I downloaded the compiler so I could compile this. When you install it, it doesn't come with a lot of the tools. So and it takes this is very slow. You'll see that this the simulation of the virtual machine is very slow. So you can barely read that, but it's starting the virtual machine here. I could have saved the state, but I wanted to show you the startup. Well, what do you guys think? Well, how many do you think? Yeah, you can say it here. Why not? We're all learning. Your guess is 8. That's a good guess. Okay. What I'm going to do, I think, is open up a command window. They call it terminal in Linux, but it's a command line window. And I created, I stuck it in documents. Oh, I misspelled it. That's right. Okay. And the C code is the cat. You can see the code. I wrote it exactly like it was in the book, except I added some print lines so you could see. So what I did was I put a print line that said before the first fork, before the second fork, before the third fork, and ending the process. Okay? So each of those would put out a line. So now I'm going to, oh, and when I compile it, I made a slight mistake. I didn't include a name for the output, the compile. So the default is a.out. Normally, when you compile a program, you would pass what you want to call it. I didn't do that, but I'm going to execute that, and you can tell it's got the X on it. That means it's executable. We'll talk more about that in chapter 10 and 11 and 12, the file systems. So A out. Now, watch what happens. Okay, so I got before the first fork, before the second fork, before the third fork, end process. So this is the main program. But it spun out one fork and says there's the second fork, there's the third fork, and it spun out another process, so I got another third fork. And then I got a bunch of ending processes and finally I got another fork. So if you added up all the ending processes, 1, 2, 3, 4, 5, 6, 7, 8, you would see that there are what you said. And we just proved it. So really what a fork does is the following. I'm going to scroll up and try to get this for you. Okay, when it forks, it makes a copy of the program, but the entry point is at the next instruction for that fork. Once again, the entry point, it copies the program code, but the entry point isn't main anymore. It isn't up here. The entry point is right here for that forked process. Okay? So it's only going to get 3 of them. So when it forks again right here, it's only going to get 2 of them. And when it forks, it's only going to get 1 of them. And that's why it's 8. Does that make sense, guys? Oh, if there were 4 forks, would you get 8? Well, you would get you would get 12. Let's see, would you get 12? I don't know if that's right or not. I'd have to think it through. But it sounds like you're adding another 3, 4. Yeah, you're adding another 4. I would agree with that. 12 sounds good. You'd have to count it out. So what do we have? We have 3 forks with 8. 4 forks. I don't know if it'd be 12 or 16. I'd have to think about that. It might be 16 with 4 forks. Do you want to find out? Does anybody really care? Yeah, I'd have to edit this and recompile it. It's not that that's difficult to do. It's just I didn't want to spend any more time on this particular problem with you guys. That's okay. Okay, so I'm going to close up this. You see how slow it is? On a native machine, it's much faster. It's got to go through the virtual machine, which kind of slows it down. Okay, so it's coming off. Okay, I want to close this up. Okay, well, I answered that with you guys. I wanted you to see it so you really understood. A fork really isn't a complete copy and a complete restart of the main program. A fork is a copy of the program and a restart after the fork. So it actually has a different entry point. When we talk about programs, programs have entry points that you can create. And the operating system knows that entry point. And that's where it's going to start. In fact, where is that diagram? When we did our class example, right, the starting address of a program is identified in the program itself. Okay? And it's usually not the first, I mean, it's usually quite a few bytes in is the entry address. And that's where the operating system knows to start the program counter at. Well, if you identify different entry points in your code, like the fork would do, it would place in that new process, it would place that address right after the fork as the new entry point for that forked process. Clear? Is that clear, guys? Good. Thank you. Okay. Since we have time, did we answer the CC confer question? Oh, we should answer that. Golly, sorry about that. Let's go to the quizzes and go to the CC confer question for this week, week 3. During the demonstration of context switching with the class, Art played the role of what? What was my role? No, wow, that wasn't my role. All right. Yes. Yes. Thank you. I put the answer here. I was the dispatcher. Make sure you spell it right. Okay, let me go to grades and see if you guys are doing it. You don't have to do it tonight, but, you know, sometime. Yeah, you're doing it. You're doing it, looking good. Albert, you got it. Daniel. Claude, you did. Mega, excellent. Stephen, and Fang, you guys did good. Okay, it works. Okay. The next thing I wanted to talk to you about, we have quite a bit of time left, almost a half an hour. So, somewhere in this list of stuff, let me see if I can find it. In next week, it looks like it's in next week's. Extra credit programming project information. Okay. So, when it's a zip file, when you unzip it, well, let me illustrate it. I'm going to download it to my desktop. And I'm going to open it. No, I didn't want to do that. I want to open the folder it was at. Alright, we got to go find it. There it is. So you would right mouse click and open with Windows Explorer. That's the best way to open if you don't have a zip file. And then just right mouse click, copy, and you can close that window and you can paste it where you want to put it. I'm going to put the thing right there. Okay. And I'm going to delete these later. But I'm going to open it up. You have 4 files. So we'll first look at the document file. So the Special OS Simulation Project, worth up to 20 points. It comes from when I was teaching CIS31 back in the 1990s. The class was Design and Implementation of Operating Systems. You may write your program in any language. I've provided C headers. So operating system, data structure header is what I've provided. You don't have to use it. But it defines the data files that I provided. As part of the file, I included the operating system data structures needed, so I included that. I put a comment block, which should be at the beginning of your code. Comments of each routine I created, of course yours will be different. So I tried to tell you by my comments all the different routines I used in my program. The idea is to create an operating system that simulates activity of a real system. It reads 2 data files. The first one is the OS parameters. Each record would be a new simulation of your operating system executing. And 2, the data input. Each record would be a program with its runtime characteristics, CPU, I/O needs, etc. You'll need a clock cycle feature that counts from 0 to n. Each CPU unit is a clock cycle. Each I/O unit is a clock cycle. It makes it much easier like that. Events would be scheduled based on the clock. Oops. I've provided a sample of the printed output at the end of this document. I've provided the 2 data files needed. It's this one, OS operating system parameters.dat. That's the parameter file that you'll have to play, and then operating system input data file that you'll have to read. And so the idea is, this is the data. The operating system parameter files look like this. So there's 4 records, and they're showing memory mode. Memory mode fixed or variable. What's the size of the blocks? The number of blocks you have, how many processes can you process at a time, what is your process algorithm. We're going to talk about these in chapters 5, 6, and 7. What's your quantum size? Okay. How many disk units do you have? How many tape units? How many CD units do you have on your system? And you're going to print the current status of everything every n units. And so every 50 units, in this example, you'll print the status. Now the next thing is the input data. I've got 10 programs. Got all these program names, how much memory each program needs, what's its initial priority, and what is the runtime characteristics. What this means is 10 CPU units, 20 units on device 1, 8 units, 20 units on device 1, 8 CPU units, 20 units of device 1, 10 units of CPU, 20 units of device 1, 8 units of CPU, 20 units of device 1, and then finally 8 CPU units, and it ends. And they all go like that. Okay, some have less number than others of their runtime characteristics. So here's what the output would look like. You'd print out your data. So this is the data coming in. You print it out so you can see that that looks good. Okay, so that's printed out. Let me go through this a little faster. Okay, so that's the first output. Now it's starting the simulation. So based on the rules of the first operating system, here's what we want. We want fixed memory, 5,000 block size. Maximum we're going to get is 20 blocks. So that's how much is available. 20 blocks of memory. We don't have any more. We're not doing variable. The maximum number of tasks I'm going to allow is 10, and we have to have 10. Which algorithm we're going to use? FIFO. How many disk units, tape units, etc. we have. Disk is unit 1, tape is unit 2, and CD is unit 3 of the numbers. And then we allocated this program at this time, because the operating system takes time to do things. So it took, and we gave it a PID of 1. So this good program has a process ID of 1. And we're in cycle 3. Okay, because the OS takes 2 cycles of this to do everything. It might take more. And what memory blocks we assign. Okay. We can't run arts class because we have enough memory, so we flushed it. And we allocated another thing that we could run. Same thing, looks like we're doing this all at this time frame. We're allocating. So this is the master schedule. Then the dispatcher started this at 9, started bar none at 19, started we only have one processor. Way to go at 34, overdue at 49, and there's a snapshot of the system at 50 units. So you can see there's 4 executing. This one's taking up these memory blocks. The current state is this guy's ready. These 2 are blocked on an I/O. This guy is executing. And this is where this guy is in the ready list. And the I/O tape device, this is blocked on device type 1, device number 2. And this is type 1, device number 1. And when is this going to have an event? You have to have some kind of way of triggering the end of each of these events. So the interrupt is going to occur for this device at time units 83. The interrupt for this device is going to be 148. And then the timer interrupt should be at 60 for this guy executing. So you kind of know when these guys are coming back. Okay. And then again, you have that at 100. Then 150. You can see how this is pending an I/O. So basically, pending means it's waiting for one of these devices, but they're used. So it's pending an I/O. There's 200. Oh, here's something that completed. See, we completed good program at 333, and we deallocated good program at 336. And there's the total number of service units we gave it, the total number of CPU units, when did it start, when did it end, total elapsed units, memory blocks used. So it's kind of like at the end of deallocating, you display this information. Now I'm going over this rapidly. I'll go over it again with you guys, but I just wanted to share with you kind of what this special project was about. Have other students done this? Yes. Have they done it successfully? Actually, yes. Did they use C? One guy used Java. I think another guy used C. But you can use any programming language. And then you see a number right here, what's running. I've got more things running. I've got 2, 3, 4, because 1 finished. 2, 3, 4, 5, 6, 7 running right now. And I've got in the ready list, it looks like XO is first, and hot stuff is second. And these are the events that are going to come back. for executing, we're going to interrupt it with a timer interrupt at 1:52. Okay, and so I'm going to just go through it real quick, and at some point we're going, yeah, right here, we're starting our second simulation. We finished with no one man right at 1580. Okay, and we had our last clock pulse at 1582 because the operating system had nothing else to do. So it finished at 1582. And the purpose of doing this simulation is to see if you change some of the rules here, what's the effect on the same job mix, the same program mix. Will it run faster? Will it run faster? And that's part of what the simulation does. You could put any kind of simulation parameter to find out, well, does it run faster? Let's just look at this example. This guy's in the 1600s, 1700s, 1800s, 1900s. Wow, this one ended at 2043 on the same exact requirements because we probably compressed something. We made some kind of a change in the operating system parameters. Just to give you an example. Okay, and it goes on like that. Any questions on that at this point? Okay, the other two files are data files. I'll show you this file. I'm going to open it with Notepad. Okay, so you're going to have this block information that I'd want. And I included some C headers, and I included some constants that I use. You don't have to use those. And some other constants. And the different devices. The disk was number 1, tape was 2, and CD was 4. I had a queue called ready, execute, block, done, held, and no queue. We haven't assigned it anything. And then the file definition. So you need to have these. If you're going to read the file that I provided, because it's a binary file, it's not a text file. So there's the operating system parameter record definitions. And then this is the input definitions, input process definitions. Okay. You had a two-dimensional array, up to 10 sets of CPU, I/O units, and the I/O device type. Okay. And then there's the data structures that I use. You don't have to use the same data structures, but I use those data structures. They're very simple compared to what's really in the operating system. And then these are comments from each of the routines that I created. Okay, so it might lead you along with how to write your program, or at least what could be in there. Okay, that's available to you. The last thing are the data structures, and these are in binary, and I'm going to give you this program so you'll have a hex dump program for yourself. I wrote this, it's in DB.net, but it dumps the program's data. So if you look and analyze this, you would see that this particular data file, it has the good program, and it's got the arts class. And if you look at the data, you can see the numbers and how they work here. Okay, so that's a binary file. That's why you needed the structures. Okay, you could do it from a text file, but you'd have to, you know, take this. You'd have to take this stuff here, right? These things, and put them in a text file and process it that way. You could do that with these too. I just gave you the data in a binary format. Be more fun. So, it might be a little overwhelming at this point, but you don't have to worry about it at this point. I'm just introducing. If you're interested, you could explore it a little. If you're not interested, don't worry about it. It's just to provide you with more knowledge. Okay, let's go back to the agenda for today. It's about a quarter after. We got about 15 minutes. Are there any questions that I can answer for you guys? Okay. Yeah. I don't want you to feel like you're this is overwhelming, this last 15 minutes of discussion. It's only for people who really want to play around with that. Because we're going to cover most of the algorithms, and we'll cover them at a high level, not a programming level. Okay, you have everything you I think need. If there's no further questions, I'll just say good night to you all and have a great weekend. I hope you had fun tonight. I did. Thank you. Thank you all for participating. Yeah, I plan to enjoy the weekend. You bet. Thank you, Megan. You too. Have a good weekend.